Hello everyone and welcome to today's lecture on the topic of task scheduling. Well, we introduced some basic principles and algorithms for scheduling, particularly mostly used in real-time operating systems. Right. So first off, let's start with what is exactly scheduling. It's the process of assigning system resources, networkings, compute units, etc., different accelerators, right, to perform tasks. So whether that's computing, data transfer, listening to I/O, and others. So I have included, as part of this presentation, some references. So we have reference 1, 2, and 3. At the end, there is a slide listing all the references where you can find the specific books or materials that I'm referring to for any further reading. So if you see numbers like this, don't get confused. You can go towards the end and see exactly where you can follow up on this information. Right, so scheduling is carried out by a special operating system module called a scheduler, which is designed to utilize all system resources, also called load balancing, and it's optimized to achieve a certain quality of service target, whether it's maximum minimum runtime or optimizing energy consumption or others. And it can also help facilitate multi-user system access. So you can see that the scheduler can be quite complex in your everyday, so user-driven operating system like Linux, Windows. You can have multiple schedulers. Like you can have short-term, medium, long-term schedulers depending on the type of the task that needs to be scheduled in, right? For the rest of the presentation, instead of tasks, I will use threads. And for scheduling, all of them, like we assume that the scheduler starts with a queue and pool. So how the threads go in the pool, it's another topic. The scheduler performs context switching when assigning multiple threads to one compute unit. So context switching is essential when we do scheduling. So I also want to talk about that a little bit. What exactly is context switching? Is the process of storing system state of a particular thread, right? And it allows multiple threads to use the same compute unit so that a task can be paused and resumed at a later date. And it's essential to multitasking. So what that means is that if we have two threads, say thread 1 and 2, if thread 1 is running on the device and there something happens, right, or higher priority thread comes in and needs to be scheduled immediately, we can actually save the system state, which includes copy of the contents of the register file, or thread priority, the execution time, and other information associated with the thread. We put that on the stack. Then we can safely load all of these variables for thread 2, execute it, and then when it comes time to come back to thread 1, we can just pop it from the stack, or like other specific structures, again, out of the scope for this lecture, and we can continue executing thread 1's code from where we left off, right? So obviously this is essential. We need to know where we left off so that when we come back to the thread, we can just resume. So it's very, very important. And context switching puts the thread ID back in the queue. So these are kind of basic principles of scheduling that I introduced. Again, you can look at the relevant literature that I've listed in the lecture if you want more information about this. The main focus of this lecture, though, is to look at specific scheduling algorithms, right? So that's what we'll be covering. We have, in general, two types of scheduling. We have cooperative scheduling and preemptive scheduling, right? Cooperative scheduling involves the scheduler does not perform aggressive context switches, right? The threads are issued one after another, or when they voluntarily yield control, or are either idle or blocked, right? It requires the threads to cooperate, hence the name, right? And high priority threads must wait for low priority ones to finish before they can be issued. Obviously, in system critical applications, high priority threads need to be given the highest priority to execute first. The cooperative type of scheduling is not used in modern operating systems in general. What we'll be taking a closer look at is preemptive scheduling, where the scheduler can temporarily interrupt a currently executing thread to schedule another, right? So that's why we need context switching. So that when we come back to it, we can just resume the work with the preempted thread. It requires context switching here. Higher priority threads are actively issued, interrupting low priority ones. This is used in most modern operating systems, and examples of threads with raised priority that can immediately preempt others, right? So interrupts, whether it's some timer or I/O call, operating system calls, and others. So complex operating systems have a lot of more advanced features where things need to happen immediately. And in real-time operating systems, some of those are even more critical, right? So now we're going to look at basic scheduling algorithms for this type of preemptive scheduling, right? So we have, again, two types. We have fixed priority scheduling and we have dynamic priority scheduling. Fixed priority is commonly used in real-time operating systems where each thread has a pre-runtime computing starting priority, right? We'll have examples where you know what that means, like pre-runtime computing. The compute unit executes the highest priority thread in the queue for a given time slice, right? Though the fixed priority scheduling is vulnerable to thread lockout, which means that threads with higher priority can constantly keep preempting low priority threads, and they could get very, very little runtime. So an example of this type of scheduling is rate monotonic scheduling, which we'll look at closely in today's lecture. And we also have dynamic priority scheduling, in which the thread priorities are calculated during system runtime. The thread queue is updated dynamically, right? So yeah, that allows for a lot more flexibility in scheduling as well. Allows schedulers to adapt quickly and obtain an optimal configuration when conditions change, right? An example of this type of scheduling is the earliest deadline first. Okay, so first, let's look at the rate monotonic scheduling, right? So this is the fixed priority scheduling example. So in the RMS scheduling, each process is assigned a unique priority P based on its release period, right? So that's the period of the thread. And the shorter period, the highest priority. For example, we have threads 1 and 2. So if thread 1 occurs more often than thread 2, then it has higher priority. We can also test whether a pool of threads can be successfully scheduled using this formula. It's not the only one. There's a few others. This is just, there is some more complicated math behind this. But what this formula basically means is that it looks at thread utilization, so given by you, and the utilization for each thread in the pool. So say we have a pool of n, and we have 1 to n threads, right? The utilization is defined by the worst case execution, C, divided by the release period, right? So this basically means how much of the compute resources the thread needs to occupy at a given time slice, right? So we calculate the sum of all of these for each thread in the pool. And if, for example, for 3 threads, so we plug the number of threads in the right-hand side of the equation. And for example, for 3 threads, we get 0.78. We need to be less than or equal to this number. Again, this is just one of the equations in order to kind of guarantee that using the rate monotonic scheduling, we can successfully schedule this pool of threads on our compute unit, right? This equation is not perfect, and I'll give an example later on, but this is a good guideline just by looking at your current pool, whether we can use this algorithm or not. Okay, so this is our first example for rate monotonic scheduling, right? So we have 3 threads. These are the thread periods. This is the compute time required for each thread. So the first thing we do is calculate the utilization and then the priority of each thread. Again, the priority is tightly calculated, right? So that means that it's based on the period. So in our example, thread 2 has the shortest period, so it needs to occur every 3 compute cycles, right? So again, everything is abstracted. You can scale this up or down, megahertz, gigahertz, whatever you want. We're just looking at the general picture here, right? And we assign it with the highest priority. So again, if you think of it as a thread queue, at the bottom of the queue, first would be the highest priority, right? So priority 1. And then the second priority is the first thread, and the third priority is the third thread, because just based on their period. We calculate the utilization, 0.73 less than 0.78. So it is possible to schedule this using the algorithm. So let's try and do that. So again, thread 2 comes in. Every 3 compute cycles, we schedule it for 1 compute unit, right? And obviously we're looking at the time slice of the longest period of the threads here, because this is repeating, right? So as long as we can repeat this, even if it doesn't quite line up, we should be able to schedule for the other time slices of period of 10, right? So then we schedule the second priority thread. So that means that for every 5 compute cycles, we issue 1 compute unit. So again, we try to utilize the system in the maximum capacity. So the first time we find a free slot, we can schedule the thread and so on and so forth. So the aim is that for any time period, we don't get more than 2 threads being high, like scheduled, right? And then for the third thread, the first available slot for it we find here, and then the second available slot we find for it here, right? And we've successfully scheduled all our 3 slots for our time period of 10. Great. So let's have a look at the second example. Right. So this is just a highlight that the aim is that for every time slice, we get something like this, where we have issued only 1 thread and the remaining are not issued. If you get, obviously, 2 being issued, then there's a violation because we're scheduling for a single compute unit in these examples. Okay, so let's look at the second example. So we calculate the utilization, calculate the priority of the threads based on the period, and we see that the test doesn't quite hold up, right? So even though we're under maximum utilization, which would be 1, right, is the maximum, we're scheduling for a compute unit of 1, so anything under 1 should be schedulable. But because of rate monotonic not being super optimal, you can see that there's cases where that's why we need the maths to kind of double check whether we can schedule or not. And so we refer to the equation, we see 0.80. Let's try anyway, right? So we schedule the first priority thread. Again, every 3rd period, we schedule 1 compute unit on the device. Compute unit worth of work on the device. Then we move on to the second thread. Again, the next best slot. So we need to fit 1 every 4. So we fit 1 here, and then we fit the next one immediately on the 5th compute unit cycle, right? So then for the rest of the remaining slots, we need to fit in the final thread, the second thread, right? But, so we need to schedule 2 compute units worth of time, but we only, so in this time slice, we only have 1 slot available for it. So just extending that, the next time we can schedule it would be time 6, right? But this is out of our period here. So we've kind of violated the scheduling requirements. And the system will crash because we haven't issued our thread enough compute units worth of time on time, right? Within the 5 periods that we're looking at. Okay, and this is a third example. We will go over it during the next live session. So I'll go over it with you live together. But I encourage you in the meantime to go alone and try to attempt this on your own, all right? So the next algorithm we're looking at is the earliest deadline first scheduling, where the threads are given priority based on the deadline, which enables dynamic priority preemptive scheduling, right? So if the deadline for thread 1 is less than the deadline of thread 2, then it has higher priority. And you can see that the priority of the threads is not pre-computed like this, where we just look at the table and we can calculate the priorities. This is more dynamic. So this is a schedule based on Holmes' rule, and you can look at the reading material for further information, where It says, given a set of n independent tasks with arbitrary roll times, any algorithm that at any instant executes the task with the earliest deadline among the ready tasks is optimal with respect to minimizing the maximum lateness, so that we ensure that the tasks complete as quick as possible, right, within a given time slice, by issuing for the earliest deadline first, right? The schedulability test for this algorithm is simply the total utilization of the thread pool, right, does not exceed system capability, which is in our case 1, because we're issuing to a single compute unit in our examples, right? So let's look at example 1. Again, we have 3 threads, we have 3 periods, we have the worst case execution time requirements, right? So in our little time chart here, right, scheduling figure, we'll try to schedule as best we can for period 5. You'll notice that this is exactly the same problem as example 2 from the rate monotonic. So we'll try to actually solve this and successfully schedule it, use it earliest deadline first. So let's hear how that works. First, we calculate the deadlines. So because of the period, we know that the deadline for thread 1 is, so we need to complete it by cycle 4, cycle 8, 12, right? It's repeating, right? Again, this is an example of repeating threads. You can have non-repeating threads that come in and go, but you need to look at the deadlines then. And then we've done for all the threads. We've calculated the utilization. Again, it's 0.98, which is less than 1, so we should actually be able to schedule this successfully on our compute unit. So let's give it a go, right? So first, we'll look at the first few deadlines, right? The deadlines here. So the first one, the first deadline here, so you can see that priority changes. First deadline that we need to satisfy is for thread 3. So on the first compute period, we issue that. Then the second deadline we need to satisfy is 4, right? And it's done. So this is done. So we've within the time slice, we've issued 1 compute unit, satisfied the deadline, it's good. Third one, again, we issued 1 compute unit, satisfied the deadline, we're great. So the next one that we need to look at is thread 2, right, where we need to issue 2 compute units by the deadline. We do exactly that. And then the next set of deadlines, right? So the next deadline is 6. So we need to issue 1 compute unit before the deadline. Great. We have a remaining slot, so we issue that. And this time, we've actually successfully scheduled all threads by adhering to the principle of earliest deadline first algorithm, right? But as you can see that every time we go up in a time slice, we have to look at these deadlines, and we can't actually predict the priority in advance, as we can do with the rate monotonic. So this is an example of dynamic scheduling algorithm. So I've also left an open-ended example for you to complete on your own. Again, during the next live session, we'll go through this together, but you should try to, as best as you can, do this on your own, and then we can compare it to the right answer next time. Right. So again, this is the slide with all the additional study materials. If you have any further questions after the lecture, you can send me an email, or you can go do some reading on your own. The first 3 are books, so there are specific chapters on scheduling in there, and 4 and 5 refer to specifically the rate monotonic and the Horn's rule, right? Okay, that's all. I'm open to questions right now, and if not, see you all next time. Thank you.